U-Substitution for definite integrals.
Alright, so in this example, we're evaluating the integral from 0 to 2 of x squared times the square root of x cubed plus 1 dx. So here I have an inside function of x cubed plus 1, and I can see that a modification of its derivative being 3x squared, is being multiplied here on the outside. So I have x squared dx. So I should think use substitution, but we do have these limits of integration. So we're actually going to need to add a step to the previous set of rules that we followed for solving an indefinite integral with U-substitution, but we're also going to remove a step as well. So it's about the same amount of work, just a little bit of a different method. So let's go ahead and start by letting u equal x cubed plus 1, and then du will be equivalent to 3x squared dx, but I'm only interested in x squared dx, so let's go ahead and divide both sides by 3. So we're going to have 1/3 du equals x squared dx. So that's exactly what I'm going to need to replace up here, is the x squared dx, and then I have exactly x cubed plus 1 that I can replace with my u. So all of that looks exactly the same. All of that looks great. So in fact, let's go ahead and start filling some stuff in here. So x squared dx is going to be 1/3 du. So let's go ahead and bring the 1/3 to the front, and then we will go ahead and leave the du in the back. And then let's replace the square root of x cubed plus 1 with the square root of just u. So this is now the square root of u du. Now, the easy thing to do, but it would be incorrect, is to just carry on or carry over these limits of integration. So just to go ahead and put 0 and 2. But we have to be really careful. These limits of integration, even though we're not writing it out like that, it's implied that these are on the x-axis. So this is really an x equals 0 to an x equals 2. And we're going ahead and switching over to the variable u. So we have to switch the limits of integration to u equals values. And how we're going to do that is we're going to plug the limits of integration into the u that we chose to be our change of variables u, our u of x. So in other words, I need to find u of 0. So that means plugging 0 into this x. So u of 0, 0 cubed plus 1, is 1. And I need to go ahead and substitute in 2. So u of 2 is going to be 2 cubed plus 1, which is 9. So my new limits of integration are now from 1 to 9. So now, the nice thing about using substitution method on a definite integral is that once I've chosen my u, I've found my correct du and made my substitution, including the change of variables. Once I have this new integral, I don't have to care at all about the original problem I was trying to solve. It's as if I've created an entirely new problem for myself. So I never have to go back and worry about plugging in u equals x cubed plus 1. I've gotten rid of that by changing everything to be in terms of u. So now I'm solving this brand new problem and acting like that's what I started with. So the answer here is going to solve this original problem that I had, but this is going to be a lot easier to solve because the antiderivative of the square root of u is something I can evaluate using the power rule. So let's keep going here. I have 1/3, the integral from 1 to 9, so I'll drop the u equals, of u to the 1/2 du. So this is 1/3 times, the antiderivative here is u to the 3/2 times 2/3, and I'm evaluating this from 1 to 9. So now this is 1/3 times, now let's go ahead and plug the 9 in, so we get 2/3, 9 to the 3/2, minus 2/3, 1 to the 3/2. And let's keep evaluating here. So I have 2/3 times 9 to the 3/2. So at this point, we should have a lot of practice in solving something like this. So this is 9 to the 1/2. So that's the square root of 9. So that's 3. And 3 cubed is 27. So I have 2/3 times 27 minus 2/3. So now what I have is 1/3 times, here what I'm going to do is, since I'm going to want to subtract these two quantities, I'm going to rewrite 2/3 times 27 as 54 over 3 minus 2/3. And that's going to give me 1/3 times 52 over 3, or finally 52 over 9. So I can go ahead and leave my answer like this as 52 over 9, and that's it. I'm done. I solved my original definite integral with the substitution method, but the nice thing is I didn't have to go back and plug u equals x cubed plus 1 in ever again like in indefinite integrals, because I made the change of the limits of integration to be in terms of u as well. So that's going to be the additional step we throw in, but we throw out the going back and replacing u with x cubed plus 1. So I definitely at this step right here, do not go back and replace u with x cubed plus 1, because you're going to completely throw off the answer now that you've changed the limits of integration to be in terms of u. Alright, in this next example, again, we're going to use U-substitution with limits of integration. So solve a definite integral. So the definite integral from 1 to 3 of x over x squared plus 1 dx. So just one quick thing to clarify, we cannot rewrite this as x over x squared plus x over 1. That does not work. These two integrands are not equal. So only if I had x squared plus 1 on the top and x on the bottom could I use some algebra first. So let's talk about why first that didn't work. So what I do want to recognize though is that I have this fraction, and if I let u equal x squared plus 1, then the derivative would be 2x, and I have an x dx which is only off by a constant, so u substitution is the strategy I want to use. So let's go ahead and let u equal x squared plus 1, which would mean du is 2x dx. I'm only interested in x dx, so let's multiply both sides by 1/2, making 1/2 du equal to x dx. So now I'm going to go ahead and rewrite my integral as the integral from, so here's where I have to be careful, it's not the integral from 1 to 3. So right now, let's just go ahead and pause and find the new limits of integration. We're going to go ahead and plug 1 into u and get 1 squared plus 1, so I get out 2. And then I'm going to plug 3 into this u function, so I'm going to get u of 3. So 3 squared is 9 plus 1 is 10, so my new limits of integration are from 2 to 10. And then I'm going to want to replace x dx with 1/2 du. So let's go ahead and put the 1/2 du in. And then I'm going to want to replace x squared plus 1 with u. So I'm going to have a 1 left over on the top over x squared plus 1 was u. So now let's go ahead and try to solve this definite integral here. So I have 1/2 the integral of 2 to 10 of 1 over u du. So this actually has that nice formula. Let's go ahead and carry over the 1/2. The antiderivative here is the natural log function. And remember that nice little shortcut formula said we can do the natural log of b over a. So the natural log of 10 over 2, or 1/2 the natural log of 5. And that would be our final answer to this original problem here. So a very nice little shortcut that we can use was rewriting this as natural log of 10 over 2, but we could have found the general antiderivative and then combined to get the same answer. But the key is to applying U-substitution, but not forgetting to rewrite the limits of integration to be in terms of u. So these were x equals, and now they are u equals. So they match the variable that we were integrating with respect to.
Alright, let's look at another example. The integral from 0 to pi of 2x cosine of x squared dx. So I'm going to go ahead and choose my u to be x squared. My du would then be 2x dx. And I'm going to need to change my limits of integration because right now they are in terms of x. So x equals 0 and x equals pi are my limits of integration. So they are going to have to turn into u of 0 is going to be 0. So plugging in a 0 here and squaring it gives me 0. And u of pi is going to give me pi squared. So my new integral is going to become the integral from u equals 0 to u equals pi squared. And let's go ahead and make our substitution. So my u is going to be right here for x squared, and then my du is 2x dx. So my integral is going to become cosine u, and then 2x dx is exactly du, so cosine u du. And now we can forget that this problem ever existed because I changed my limits of integration. So now the antiderivative of cosine u is sine u, and we're evaluating from 0 to pi squared. And now I substitute in my top limit of integration first, so I have sine of pi squared minus sine of 0. Sine of 0 is 0, and sine of pi squared is not on the unit circle, so we have to leave our answer as sine of pi squared, or we would need to use a graphing calculator to approximate this as a decimal, but leaving it as sine of pi squared is fine. So this is not, again, a value on the unit circle, so it's not pi over 3, pi over 4, pi over 2 pi. Pi squared is not something that we should be able to evaluate without a calculator into the sine function. So we can just leave our answer as sine of pi squared.
Alright, now looking at number 11 of a previous AP exam, we want to use substitution, and they're giving us the u. So using the specific substitution, u equals 2x plus 1, the integral from 0 to 2 of 2x plus 1 underneath the square root dx is equivalent to, so they're not even asking us to solve this. They're asking us, do we understand the change of variables that occurs when I have a definite integral? So the integral from 0 to 2 of the square root of 2x plus 1 dx is what I'm interested in rewriting. So let's let u be as given 2x plus 1. Then du is 2 dx. I only want dx, so 1/2 du equals dx. So now I'm going to have that this integral is equivalent to 1/2 the integral from, and now here's where most students are going to make the mistake. They're going to go ahead and write from 0 to 2, and that's not correct. I have to change the limits of integration, so I have to evaluate u of 0. So plugging 0 in for x, I'll get out a 1, and then I have to substitute in the upper limit of integration. So 2 times 2 is 4 plus 1 is 5, so my new limits of integration are from 1 to 5 of the square root of u, because 2x plus 1 was my substitution, u du. So this definite integral is equivalent to, with this substitution, it looks like c. So the integral from 1/2, or the 1/2 times the integral from 1 to 5 of square root of u du. So they didn't even ask you to evaluate this integral, they just want to make sure that you understand the substitution method with a definite integral. So the answer is C.